To be able to wire our circuit in a breadboard, let us first understand the interconnections within the breadboard. And shown on this lower bottom corner is the internal connections of our breadboard. So here we see the power rails, these horizontal interconnections over here. So there are two power rails at the bottom and two power rails on top. As you can see here, the upper power rail is positive, while the bottom power rail is negative. Now, it's also important to realize that we have here our center divider, or in the actual breadboard, we will be able to see a ravine at the center of our breadboard. And on top and at the bottom of that ravine are interconnections that are connected in a column. Okay? So you will be able to see these holes over here. So each of these holes are actually connected in a column manner. Okay? Again, take note, it is not connected on rows unlike the power rails. But this time, it is connected in columns. Okay? Meaning, these dots over here, or these points over here, are actually connected. But this one is not connected to its neighboring hole. Okay? Now, let's start our discussion on how to transfer from schematic to our breadboard. Now, shown here is our schematic diagram. Okay? We have our battery, our switch, our diode, and our resistor. Now, for the first interconnection, okay, we have here the positive terminal of our battery connected to one terminal of our switch. So where is this interconnection on the actual? Here we see the positive terminal of our battery connected to the upper power rail. Now, this is connected now to the terminal of our switch. Okay? Now going back, the other terminal of our switch is actually connected to the anode of our diode. In this case, we try to look at here, this terminal over here is actually connected to our diode since they are connected in a column here in the breadboard. Okay? Now next, the cathode of our diode is connected to one terminal of our resistor. Okay, so in this case, this one over here, these terminals over here, the cathode of our diode is connected to the resistor. Okay? And the other end of our resistor is connected to the negative terminal of our battery, which is also the ground of our circuit. So how do we compute for the load voltage, load current, diode voltage, and diode current when a diode is connected in a circuit? So this solution will actually be a theoretical approach, okay? Which means that whatever is measured may not be the same as when we solve it theoretically. But this gives us a rough estimate as to how the circuit actually functions. So in this case, we will be creating a loop current within our circuit, as in this one. Now this is the loop current that we have established. Now notice that we have actually written it in a counterclockwise direction. Now later on we will know why it is drawn in a counterclockwise manner. Let's continue the video. Now notice here that we have put a minus and plus signs on our resistor and our diode. Okay? So we have here the minus sign for our resistor, plus sign, minus, then plus. As I've said a while ago, there is a reason why the direction of our loop is directed or drawn in a counterclockwise manner. And this is the reason why. If it is drawn in this manner, starting from here, it will actually hit our battery on the positive side. Meaning, in the circuit analysis later, this will be positive 9 volts. And after that, it will hit our resistor. And since our resistor is actually a power-consuming device, then we will be establishing, or we will write here, a negative. We will write first the negative, then positive. Now next, when we pass by our diode, we will hit the cathode first. And it goes without saying that this part of our diode is actually the negative part. Okay? And after that, we will be passing through our anode, which is the positive side of our diode, or the P-type material of our diode. Now let's continue our solution. Now we start our solution by using Kirchhoff's voltage law. And it states that for a closed-loop series path, the algebraic sum of all the voltages around any closed loop in a circuit is equal to 0. Now notice the word algebraic, meaning in this particular analysis, it will involve positive and negative values. And that is where the counterclockwise direction that we have employed a while ago can be used. So how do we solve this one? So notice that as our loop current rotates in this particular circuit, it actually hits the positive of our battery first, then the negative of our resistor first, then the negative of our diode. Okay? And so the equation will be as follows. As we can see in this first equation, okay, we have said a while ago that it will be positive 9 volts for the battery, negative voltage for our resistor, and negative voltage for our diode. Now notice that the switch is not included since it does not, okay, it does not have any voltage drop. So this is our equation. Okay, now the VR there is the voltage of our resistor, and VD is actually the voltage across our diode. Okay, now continuing our analysis. Here in this particular part of our solution, we can see that we established or we reviewed an equation that is part of Electro 1, and that is that voltage is equal to the product of the current and the resistance. Okay? And the diode that we are using is actually a 1N4007 diode, which is a silicon diode. And as such, its diode voltage is approximately 0.7 volts. Now we will be using it on the next parts of our solution. And so this is the next part of our solution. Okay, again, we hit the positive side of our battery first since our direction is counterclockwise. So this is positive 9 volts, which is this one. Okay, then minus the voltage of our resistor. Okay, in this case, since we established that voltage is equal to current times resistance, okay, it will be the current that passes through our resistor, which is represented here by the variable IR, okay, the current that passes through our resistor, times the resistance of our resistor, which is 1 kilo ohm, okay, minus the diode voltage. Since it is silicon, as we have said here, then it is 0.7 volts. Now this is equal to 0. Now, as you can see in this equation, we have only one unknown. So since we have one equation and one unknown, we can solve the value of this missing term, the I sub R, or the current that passes through our resistor. How do we do that? Let's continue our solution. Now here we see that there is a need to transfer this term to the right side of the equation to make it positive. Okay? Then we will be able to subtract 0.7 from 9 volts. Okay? As such, we have 8.3 volts is equal to IR times 1 kilo ohm. Now again, notice that IR times 1 kilo ohm became positive, and 8.3 volts is a result of subtracting 0.7 from 9 volts since they are of opposite signs, 9 being greater than 0.7. Now dividing both sides by 1 kilo ohm, we will now be able to solve the value of the current that passes through our resistor, and that is 8.3 milliamps. This is now our result. Now notice that voltage divided by ohm is actually amperes, and 1 divided by kilo is milli. That is why the result is 8.3 milliamperes. Now to continue our solution, let us now solve for the voltage across our resistor. We have said a while ago that that is the product of the current that passes through our resistor and the resistance of that resistor. That's what we are doing right now. So since we have already solved the value of the current that passes through our resistor, and we have the value of our resistance, which is 1 kilo ohm, then we can solve the value of the voltage across our resistor. So that would be 8.3 milliamps for the current and 1 kilo ohm for the resistance, which gives us 8.3 times 1 is 8.3. Milli times kilo cancels out. Ampere times ohms is volts. That is why the result will be 8.3 volts. It says here in accordance with 2. As we can remember on our notes a while ago, currents in series circuits are actually the same. That is why the current that we solved a while ago, which passes through the resistor, is actually the same as our loop current, the one that we have drawn counterclockwise a while ago. And this is also the same current that passes through our diode. And as such, the value is 8.3 milliamps. This current is also the current that passes through our power supply, or in this case, our battery. And these are now the solved values for currents and voltages. Now next, let's solve power dissipation. So again, power dissipation means that it is power that is wasted. Remember that diodes are actually functioning as a switch, meaning ideally it must not consume any power at all. Okay? But since there is a minimal amount of voltage, which is our potential barrier, and there is current passing through our diode, then it consumes a certain amount of power. Now that will be the power dissipated by our diode. Also in this case, we are using a resistor to act as a load. Now take note of the word act, meaning resistors actually in real life does not function as a load. Okay? Oftentimes, it is used to actually control the current that passes through our main load. Okay? So in this case, that's why the term is power dissipated. And we will be also solving for the power supplied by our battery. Now you may notice later that the power consumed by our diode plus the power consumed by our resistor is equal to the power supplied by our battery, as in the law of conservation of energy. Okay? Energy is not created nor destroyed, it can only transform from one form to another. In this case, the power of the battery is consumed by our resistor and our diode. As you can observe here, we are solving for the power dissipated on our diode. And the formula is the voltage across our diode times the diode current. Now we all know that our diode is silicon, so that's why the voltage drop is 0.7 volts. Now the diode current, as we said a while ago, is the same as the current across our loop and the current in our resistor, because it is connected in series. That is why it's 8.3 milliamperes, the same as here. Now calculating. Now using our calculator, we'll actually arrive on an answer of 5.81 milliwatts. Now why is it milliwatts? A volts times ampere is actually watts. Now since there is a milli over here, then it will be milliwatts. Now using our calculator, okay, 0.7 times 8.5 will be, or 8.3 will be 5.81. We have here milli, so milli volts times ampere is equivalent to the unit watts. That is why our answer is 5.81 milliwatts. Now continuing our solution, so here we will be solving for the power dissipated by our resistor. Now PR here is equal to voltage across the resistor times current that passes through our resistor. So the VR, as we have solved earlier, is 8.3 volts, which is over here. And the current, IR, is actually 8.3 milliamperes. Now, when we multiply 8.3 to 8.3, we will have 68.89. Again, we have milli over here. So, milli, then volts times ampere will be watts. That is why our answer is 68.89 milliwatts. Now, lastly, we will be solving for power supplied by our battery. So here we see that the power supplied by our battery is equal to the voltage of our battery times the current that passes through our battery. Okay? So the battery is 9 volts and our current is 8.3 milliamps. giving us a total power supplied of 74.7 milliwatts. As what we have said a while ago, if we add this 5.81 to the 68.89, by law of conservation of energy, this must total to 74.7 milliwatts. And these are our theoretical answers to our circuit. Now, later on, this video has actually a tandem video, which is a video on the actual circuit or the actual interconnection of this particular circuit. So, in that particular video, you will be able to compare the difference between the theoretical and the actual, okay? Particularly on the diode voltage values, okay? And actually, this particular solution is actually lacking. So you can see here, we only used 1 kilo ohm resistor. But actually, on the actual, we will be using 2.2 kilo ohms, 4.7 kilo ohms, and 10 kilo ohms. So what are the diode voltages? What are the diode currents if we use the theoretical approach or the theoretical circuit analysis? So one of the things that you will be able to find there is that here, we are actually using a constant value for our diode voltage, which is 0.7. But on the particular video, on the actual circuit, okay, you will observe that the diode voltage changes. Okay? What causes this change? So you will be able to find out on that particular video. And that ends our discussion for this session. In this video, we have learned how to use the schematic diagram in order to wire the circuit on an actual scenario. Also, we have learned the various symbols, okay, particularly on the diode, which is the focus of our attention. Also, here we have learned how to solve for the diode voltages, diode current, okay, the current that passes through our load, and the voltage across our load. Also, we have solved for the power dissipation of our resistor and our diode, and also the power supplied by our battery. That would be all for this video, and I'll see you on our next one.